but also then you need a certificate. Okay, so now you start. I will turn off my.
Okay.
Good afternoon, dear colleagues. So I guess it is time to start our next session. And my name is Valentin Novikov. I will be chairing the talks this afternoon. And we have 8 talks until the evening, mostly in the field of molecular magnetism, obviously, with organic chemistry and coordination chemistry, again, mostly. And our first speaker in this session is Evgeny Tretyakov, who is quite known in the field of organic radicals, previously nitroxide radicals, and now he's going to talk about Verdazyl-Nitronyl nitroxide polyradicals. So, Evgeny, floor is yours.
Thank you very much, Valentin, for your introduction. I will try to start my presentation. Do you see?
Yes.
Okay. Okay. You know, colleagues, today, first of all, I would like to thank organizers for inviting me, for giving me possibility to participate at this very interesting conference. Today, I will talk about stable Verdazyl-Nitronyl nitroxide polyradicals with high-spin ground states. At the very beginning of my talk, I would like to pay your attention on very important concept, especially for scientific community, standing on the shoulders of giants. Yeah, this is very old concept traced to the ancient time, and it's important especially for us because, you know, this conception means that we have as scientists, we have a chance to see more and further than our predecessors, not because we have keener vision or greater height, but because we are lifted up and borne aloft on the gigantic statue. You know, we have many important and great scientists who found molecular magnetism field. Some of them participated at this conference, and we learned from the early works that if we want to prepare high-spin organic molecules, we have to choose corresponding radicals of hydrocarbon family, for example, 3-methyl methane diradical or methoxylenone diradical, and then to substitute very reactive CH2 group with more stable organic radicals is spin-bearing group. In previous lecture, Martin Baumgarten shown several stable persistent organic radicals, and we can use them to synthesize high-spin organic polyradicals. Many groups succeeded in synthesis of triplet diradicals. They published very famous work in which they described triplet diradicals with high energy gap between ground state, between triplet ground state and excited singlet state. They are stable up to more than 100 degrees of Celsius. They can be even sublimed and deposited via vapor on some surfaces. And now we can open so-called red way of high-spin molecules creators who succeeded in synthesis of many triplet diradicals. They are very stable and very useful for future application. In our work, we try to combine oxo-verdazyl and nitronyl nitroxide as building blocks. So we started also from hydrocarbon diradicals precursors from tetramethylene ethane, from 3-methylene methane, and from methoxylenone. And via several steps, design molecules having one oxo-verdazyl building blocks and nitrogen nitroxide building blocks. We performed synthesis of these designed compounds using cross-coupling of synthesized via several steps of iodo verdazyls with nitrogen nitroxide gold derivatives at presence of palladium, and prepared finally and isolated finally with good yields corresponding diradicals bearing oxo-verdazyl and nitrogen nitroxide building blocks. So we succeeded in growing good crystals of all the radicals of the molecular and crystal structure, and characterized them using all spectroscopy methods. I just want to show you some selected results. Let's start from voltamperimetry methods, and you see that all triradicals, they can be oxidized reversibly. Both verdazyl group and nitrogen nitroxide group can be oxidized as to reduction. Verdazyl group can be reduced, but nitrogen nitroxide building group reduced quasi-reversibly. And also important that actually a bridge between two radicals group actually does not influence on oxidation and reduction potential of these groups. What is also important, all three diradicals, they are very stable. And as you see from TG and DSC diagrams, they're stable up to melting point close to 200 degrees of Celsius. Also, if we look on magnetic properties of diradicals, you see that for the radical 1, as expected, we have domination of anti-ferromagnetic exchange interaction, and for the radical 2, we see domination of ferromagnetic exchange interaction, again as expected from our group of designer. We thoroughly to approximate of Chi-T temperature dependence, we have to choose a corresponding model. To choose this model, we thoroughly analyzed the crystal structure of all the radicals, and we analyzed intermolecular contacts. Some of them I show here, and then we performed quantum chemistry calculation. You see that we used DFT and CAS calculation to estimate intramolecular exchange interaction. In the radical 1, as expected, we have anti-ferromagnetic exchange interaction, and in the radical 2 and 3, again, as expected, we have ferromagnetic exchange interaction, and stronger one in the radical 2 with tetramethylene methane topology. Also, we analyzed in intermolecular interaction and revealed that we also have in the radical 2 and 3 ferromagnetic exchange interaction. More important that this exchange interaction actually connect the radical molecules into chains. So we applied two models, Linear-Wallis model and chain models, to approximate Chi-T temperature dependence. And the second model, chain model is more realistic because we have reasonable inter-radical exchange interaction. And using this model for the radical 2, we reviewed ferromagnetic intramolecular exchange interaction more than 50 inverse centimeters, and inter-radical exchange interaction near 5 inverse centimeters. For the radical 3, we have a little bit smaller exchange in intramolecular and inter-radical exchange interaction, but anyway, all of them have positive value. If to talk about synthesized oxo-verdazyl nitrogen nitroxide radicals, we have a champion in this series, having energy gap between ground triplet state and excited singlet state more than 100 inverse centimeter. And also we have to the radicals with anti-ferromagnetic ferromagnetic exchange interaction. So actually, we can now can combine a bridge between two radical group, and use an appropriate bridge and use an appropriate connection between this bridge and oxo-verdazyl molecule. We can easy turn of magnetic properties of oxo-verdazyl-nitronyl nitroxide radical. Also, we reviewed triplet oxo-verdazyl-nitronyl nitroxide with very large triplet singlet energy gap, more than 100 inverse centimeters. All molecules, they have very high stability. They survive at temperature more than 180 degrees Celsius. So also they can be sublime at very low pressure. So they actually can be transferred via vapor to any surface. And what is also important for series of this radical, for the first time, we found a ferromagnetic triplet diradical, which are ferromagnetically coupled in spin 1 chains. So actually, it's very interesting for us also to study magnetic properties of these two triplet radicals at very low temperature. So we are open for collaboration if somebody also interested in studying of the magnetic properties, I mean ordering properties of these triplet radicals. Please let me know, and we share samples with you. If to go further to tri-radicals, if you look to the literature, you will see that not so many high-spin tri-radicals were synthesized up to now. We can separate all tri-radicals on two groups. The first one use metaphenylene coupling units, and up to now, Verdazyl described the only one carbon-centered tri-radicals, I mean polychlorinated compounds with very high stability and also with very high energy gap between quartet and excited doublet state. Also, several years ago, Zimmermann synthesized Verdazyl tri-radicals, but he did not succeed in studying of magnetic properties of this compound. So we know only have information about synthetic percent only. Also, many years ago, Lachardov succeeded in synthesis of this tri-radical having nitronyl nitroxide group, and later Tadashi Sugawara shown that in these tri-radicals we have not so high, but anyway, ferromagnetic exchange interaction between all three radical group. Another also very famous scientist, Evgeny, Katsuinue, Polyradicals, Fernando Palacio, they synthesized next group of butyl nitroxide tri-radicals, and one of them having linear structure also have a very high energy gap between quartet and excited doublet state near 240 Kelvin. What about tri-radicals having trimethylene methane based topology? Not so many compounds were prepared up to now. So the idea was to combine through two trimethylene methane hydrocarbon prototype into one tri-spin molecules, and then to design corresponding tri-radicals, stable tri-radicals. Hijivamura succeeded in preparing all these three compounds. They have all of them have two nitronyl nitroxide building bonds and one diaryl nitroxide building block. All of them have high energy gap between quartet ground state and excited doublet state. So we asked themselves a question: could we use the same idea to combine oxo-verdazyl and nitrogen nitroxide to prepare tri-radical molecules? The synthesis is not so simple. I show you only some steps of this synthetic procedure. Actually, we condense corresponding iodide derivatives of phenylhydrazine with benzaldehyde, and then by several steps, as you see, we succeeded in preparing of these diode derivatives of oxo-verdazyl. The next step was the same as for preparing of diradical. We used cross-coupling reaction of this diode derivative with nitrogen nitroxide gold derivatives, and finally succeeded in isolation of monoradicals and of diradical with 34% yield and expected triradicals with 27% yield. We thoroughly characterized all compounds, the radicals and triradicals with all spectroscopy methods. I show you EPR data. You see that for diode derivatives for monoradicals, we have rather complicated EPR spectra with many lines. After introduction of 1 and 2 nitrogen nitroxide, we obtain narrow and less resolved EPR spectra. As to cyclic voltamperometry, you see that if you see on corresponding curves for mono radicals, for 2 radicals and triradicals, you see that we have in all compounds reversible or quasi-reversible in triradicals oxidation peak related with oxidation of verdazyl blocks, and also we have reversible corresponding to reduction of oxo-verdazyl moiety and quasi-reduction, quasi-reversible reduction of nitrogen nitroxide building blocks. So actually we have nice behavior. So using electrochemistry, we actually, for example, from these compounds can generate corresponding mono and monoradical cation and monoradical anion. We successfully found a solvent from which we succeeded in growing good crystals of di and triradicals. It was appeared that from acetone it's possible to grow good crystals, and we solved molecular and crystal structure of both compounds. Also, we thoroughly analyzed crystal structure of both compounds. I will show you analysis for triradicals. This triradical forms short contacts between oxygen atom of nitrogen nitroxide group and hydrogen atom of phenyl ring. These contacts bring molecules into ribbon, and then we have inter-ribbon contacts which form so-called dimer ribbons. And then these dimer ribbons are linked via short contact between oxygen of oxo-verdazyl and hydrogen atom of methyl group into a 3D structure having some space filled with disordered solvent, in this case with acetone. If you look on this TG and DSC diagram, you will see that triradical also have very high stability. This change related with lossing of acetone molecules. So again, this molecule is stable up to 160, 170 degree of Celsius. So again, this radical is very stable and also can be sublimed at very low pressure. If you look on this slide, you will see data of squid measurement. For the radicals, we see domination of ferromagnetic exchange interactions. The same is for triradicals. And what was difficult for us to analyze magnetic properties of these radicals, because according to calculation, we have strong enough anti-ferromagnetic exchange interaction between the radicals molecules. So that's why we have strong exchange interaction inside molecules and side molecules, and with the same order but opposite sign, we have interaction between the radicals molecules. So after some thinking and many actually calculation, we think that we have ferromagnetic exchange interaction inside the radicals, and with the same order, but also opposite sign, we have anti-ferromagnetic exchange interaction within this dimer. As to triradicals, we don't have large enough intermolecular exchange interaction, and we analyzed these compounds using two parameters only. And for this interaction, we have near 100 Kelvin G parameters, and for this interaction, we have almost 10 times lower exchange interaction. It's due to rotation of this phenylalanine link on much more angle as compared with the rotation of this phenylalanine link. So what is important, actually, we succeeded in synthesis of heterospin systems containing oxo-verdazyl-Nitronyl nitroxide building blocks. They have TMM topology. We observe strong ferromagnetic exchange interaction inside di and tri-radicals. They have, all of them, they have high stability. And what is more important, we have another phenyl ring, which also can be functionalized with radical group to obtain molecules having even a higher amount of spin inside molecules. So now we are close to preparing of these tetra radicals, and planning an experiment as a synthetic path for preparing of molecules having 10 spins, and all of them should be connected ferromagnetically. So let me now acknowledge all people who were involved in this complicated work. They are from Novosibirsk Institute of Organic Chemistry: Elena Bagrianskaya, Elena Zaitseva, Irina Bagrianskaya, Inna Shondarina, Maxim Kazan, Svetlana Zhiveteva. From International Tomography Center, Viktor Ovchirenko, Matvey Fedin, Artem Bogomyakov. Very nice collaboration we have now with Tomsk Polytechnic University, with Pavel Petunin, Pavel Postnikov, and Marina Trusova. Calculation were done in Institute of Chemical Kinetics and Combustion group of Nina Gritsan, and also I thank for financial support different funds. And I thank you for your kind attention.
Thank you. We have several minutes for questions. So who would like to start? Yeah. So Evgeny, please.
I would like. Evgeny,
Thank
you very much for your lecture. Very nice compounds you have achieved now, and your future plans are looking very promising. For your analysis of the diradical and triradical, it's amazing that the diradical has so much in the core, some anti-ferromagnetic interaction. But the G values, I was surprised that for the triradical, it goes below 2. Was that calculated, or did you measure that by EPR? In your analysis, here, 1.944. It's very rare that these radicals show a G value below 2.
Actually, it's related with, as I try to show you, maybe I missed this. Every time we obtain compounds with a solvent, with acetone molecules.
Yeah.
And after on air, every time we have loosen of these acetone molecules, and maybe this is a reason of some deviation from 2. So this is ideal G value that we have to have. But
that is from the calculation, from the simulation, or was that determined by EPR? because the
No.
nitronyl nitroxide has a larger G value than
Yeah.
2.007 and the Verdazyl has 2.004. So to come below 2 is just by the simulation.
Martin, they are from squid measurement, you know. So
Yeah.
It
Okay.
was one of the variable parameters, you know.
Right.
Okay.
Thank you.
There is also a question from Professor Coronado.
I see. Can you hear me? No, yes. Okay, then I have two questions. Well, the first one, well, thank you very much first for the talk, Evgeny. Then what is interesting also in your talk is that most of your radicals, some of your radicals are not centrosymmetric. Then from this point of view, they can also be interested from the ferroelectric point of view, not only from the ferromagnetic or antiferromagnetic point of view, but also from the dipoles, the electrical dipoles that you can have if you control in the crystal more or less non-centrosymmetric crystals. Did you check these kind of things? If you have some crystals that are non-centrosymmetric and after you check some ferroelectricity or not?
Actually, we did not check this.
No, because you have most of your systems are non-centrosymmetric.
If you are interested, we can send samples.
No, but there are some systems.
Yeah, I will write you email.
Okay. No, some of these systems are from the point of view of the dipoles, electrical dipoles, not magnetic dipoles, but electrical dipoles can have interest.
Actually, in our institute, we don't have a facility to measure this. You know, I know that you have, so we can collaborate.
Well, with ferroelectricity, I'm not. I have some facilities, not so much, but in any case, it's possible to try. Yes. The other question is about sublimation. Then some of your samples can be sublimed, and then, but when you sublime the sample, you obtain crystals, or you obtain. You can control that the film that you form is amorphous or not, or you have no control over the crystallinity of the sample. Have you any control?
We observed formation of thin crystals.
Yeah, I know, but it's possible also to try to sublimate in such conditions fast, for example, in such a way that you form a film with a very, very small size of the crystals. Then this is interesting also from the point of view of the devices. That's why I asked you that, because what is interesting is to sublime and not to sublime to obtain big crystals. That is one possibility to study big crystals, but the other possibility is to prepare films as amorphous as possible, I mean with crystallites that are quite small in order to make thin films. Then this is interesting also, and I don't know.
Yes, indeed. I agree with you. This is very interesting, but we did not concentrate on studying sublimation.
Your systems are also interesting from this point of view, because as they are complex, I assume that the crystallinity is not so good sometimes, because you have a very strong complexity from the chemical point of view, and probably the crystals grow better with simple molecules than with big molecules as you are preparing. I don't know if this is true or not. Do you observe that your crystals are small or no? Because even this kind of that can indicate an idea if you have or not possibility to prepare very small crystals.
Yes, we observed formation of very small crystals.
Yeah. Then
it's not possible to check them to compare crystals growing from solvent. I mean, parameters.
No, but from sublimation is the good thing. Then you have interesting systems. Well, it's quite nice to see this kind of system. But well, not only the magnetic properties, the radicals are important from this point of view. After for going a step forward, it's possible to do this processing, and this processing is quite interesting for the films and also for studying other properties. Then it's quite inspiring your talk from this point of view. Thank you.
Thank you.
Yeah.
Thank you. We are ready to move on. And thank you, Evgeny. And our next speaker is Dawid Pinkowicz. He's from Jagiellonian University. It's Poland, Krakow. And I see you, Dawid. Here you are.
Yep. Good morning. Good afternoon, actually. So, can I start?
Yeah, we can see it. Perfect.
Okay, I feel a little bit humbled by the previous talk by Evgeny Tretyakov, because what I'm going to say to show is a very small part of the radical family of compounds, and quite unusual ones. So I'm going to focus on Dioxothiadiazoles, and I'm going to try to convince you that it's also worth trying to investigate these systems as possible building blocks for molecular-based magnets. So first, I will start with acknowledgements. So I would like to thank my two students who contributed to this research that I'm going to show. Some of the co-workers from the Jagiellonian University, Professor Pietrzyk and Professor Rams, and also the financing agencies for the support. So here are the two students that I'm talking about, Mirosław and Pavel, and the rest of my group, which is expanding this year, and two more students will actually join. So apart from the radical systems, we also do other molecular materials, mostly magnetic. We focus on a large part of our resources goes into photomagnetic systems like this one that shows photomagnetic sponge behavior. Also, the site-selective photo switching is interesting for us, like this molecule here, octahedral ones, where we can switch independently, semi-independently iron 2 and molybdenum 4 centers, and quantum nanomagnets and qubits. We also work a little bit in this vein as well, but I'm going to talk about redox active molecules and radicals. So just a small advertisement to students who may be listening. So the major group instruments that are available to the group members, not to the whole department, are the single crystal X-ray diffraction machine, powder X-ray diffraction, and squid magnetometer. So we do the initial basic characterization, including the structure and the magnetic properties ourselves, apart from the design and synthesis of our compounds. And in 2022, there are 3 more instruments coming, so new high-end single crystal X-ray diffraction, possibly at some point with N-helix, with the helium cooling capabilities. We're also building a magnetochiral dichromation spectrometer, and we are getting a Dynacool system from Quantum Design with 14 Tesla magnet and with the possibility of recording Raman spectra down to 4 kelvins. So Dioxothiadiazoles. So what is the motivation? So we would like to make small redox, multi-redox systems, smaller than what Professor Tretyakov was showing, that show electrochemical switching. And we would like to have single component rigid molecules that have multiple radical states accessible by electrochemistry. We would like to make organic magnets, and we didn't achieve that yet. And there's a literature of triplet radicals already, as already shown, but we would like to make triplet radicals using dioxothiadiazoles. So dioxothiadiazoles actually is a large family of compounds, including thiadiazoles and their various derivatives. I'm going to focus on this small part of this family of compounds. And here are probably all dioxothiadiazoles known so far and characterized structurally in the CSD database. So there is a lot to do, and we are actually focusing on this 4 in the first row. We actually made 3 out of 4 of these compounds and characterized them. The second one is actually done by Professor Awaga from Nagoya University, I think. Okay, yes. So what is the general synthesis route towards this kind of systems? So you can see the 4 routes here. The most general one is the when you combine alpha diketones with sulfamide or BEAST DMS sulfamide. The other one that is completely useless for actually, and it leads to only one compound, involves the cyanogen. And also it's possible to oxidize thiadiazoles and monooxides of thiadiazoles using MCPBA, or to oxidize the corresponding dioxothiadiazolines to the dioxothiadiazoles. So as I said, the most convenient and more general route involves the coupling of the alpha diketones with sulfamide, or the less accessible, commercially unavailable TMS derivative. This actually is more preferential. I mean, more preferential. It requires more strict synthetic conditions. So because you have to exclude moisture from the synthesis, but actually the synthesis occur at a low temperature. And this is sulfamide is actually more reactive and leads to the dioxothiadiazoles that are not accessible via the sulfamide reaction. So as I said, our adventure with dioxothiadiazoles was inspired by the work of Kunio Awaga. reported in 2011, where he actually combined phenanthrolene, not dioxide alpha diketon, to phenanthrolene backbone with sulfamide, obtained this kind of compound, which has coordination abilities on the one side, the dioxothiadiazole, which is redox active, and also show, and it's a completely rigid molecule without any dangling chains, so easy to incorporate in systems in a rational way. And you can see from the cyclic that there is an easy way to reduce this system to a stable radical anion. So we didn't actually follow the steps of Kuniawaga per se, because we wanted to design something a little bit better, something a little bit more useful for the design and synthesis of coordination polymers with this kind of dioxothiadiazole systems. So we actually designed this dioxothiadiazole derivative based on the 4,7 phenanthrolene backbone. In this way, we achieved two chelating groups from both sides of the molecules with the possibility to form coordination chains. So the electrochemistry of this compound is still similar. You can reduce it using even iodide. And just to give you some comparison on why dioxothiadiazoles are so much better in terms of electrochemistry than thiadiazoles, there is a cyclic photometry for the thiadiazole, the blue trace. You can see that it can be reduced to a stable radical as well, but this radical will be extremely sensitive to oxygen, even traces of oxygen, because the reduction occurs at very low potential versus the ferrocene couple. So, as I said, this 4,7 phenanthrolene dioxothiadiazole can be easily reduced using potassium iodide, and here is the electron EPR spectrum in a degassed anhydrous DMF. You can see it's quite complex because you can see the coupling with the nitrogen and hydrogen atoms of the molecule. And if we actually managed to calculate the spin density on the different nitrogen atoms, it appears that the spin density on these two nitrogen atoms of the dioxothiadiazole moiety is quite high, 0.25 per each nitrogen atom. On these two 4,7 phenanthrolene nitrogen atoms, it's a little bit lower, 0.1, but still quite high, and should be useful to obtain molecular magnets with quite strong coupling with magnetic centers. So here is the structure of the potassium salt of this compound. You can see that indeed this 4,7 phenanthrolene dioxothiadiazole can form stacks, pi stacks, and the squid magnetometer measurements of the chi-T versus and depicted as chi-T versus temperature shows that there are huge, very strong magnetic interactions in the system. We only managed to simulate this behavior by using the dimer approximation, and it appears that this interaction should be on the order of minus 200 wave numbers through the pi stack interactions. So we also checked if we indeed can use these nitrogen atoms of the dioxothiadiazole 4,7 phenanthrolene dioxothiadiazole to make coordination polymers, and indeed you can actually form coordination chains with this molecule. We didn't obtain the radical-based coordination polymer yet. This is just the copper-2 with the neutral molecule with some interactions through the diamagnetic bridge. We are now working on obtaining this similar compound, similar chain with the spin on the molecule as well. So apart from 4,7 phenanthrolene dioxothiadiazole, we are also working on functionalizing the 110 phenanthrolene backbone of this compound. And the first step to do this is the bromination of the phenanthrolene, which is not really easy. As some of you may know, phenanthrolene is not really prone to any modifications. It's very inert when it comes to substitutions, but you can actually oxidize it to the phendione, which then can be brominated in the 3 and 3/8 positions. And after column chromatography column purification, you obtain these both compounds. You can close the dioxothiadiazole molecule, you can reduce it, and obtain a ppn salts of these radical anions. So we managed to crystallize all three, the unsubstituted and mono and substituted radical anions with ppn cations. you can see that the crystal structure of these compounds actually lead to the layered, it's a layered structure where anions and cations are organized in layers. And this is the case for the unsubstituted and monosubstituted compound. It's different for the desubstituted, and this is caused by the disruption of the bromine substituents, by the disruption of the CH-N hydrogen bond donor capabilities, accepting capabilities of the molecule. So when the bromine atoms appear on the 3 and 8 positions, this kind of interaction cannot occur more, and this is why the structure of the compound changes, and the pi-pi stack interaction actually overcome and control the packing diagram. And this also leads to completely different magnetic properties in the case of the stacked compound. So you can see that where as long as the layers are maintained, the flat layers like this, the interactions are pretty weak. So the hydrogen bonding interactions here lead only to very weak interactions. But if you go to the stacking interactions, we estimated it to be to minus 116. It's lower what we reported for the 4.7, but what we believe the offset between the stacks, the pi-pi stacks, actually control the magnetic interaction in this kind of arrangement, crystal packing. So after that, since Kunio-Owaga didn't report any coordination compounds with radical 110 phenanthrene dioxothiadiazole radical anions, we focus on this aspect of these radical anions, and we managed to obtain a series of compounds with copper. And you may wonder why we chose copper. Copper is quite simple. It's a spin 1/2 system, and so it's easier to analyze what's happening in these kind of compounds with copper rather than in cobalt or nickel molecules. So if you combine neutral dioxothiadiazole with copper 2, you end up with chloride breached molecule like this. If you combine a neutral molecule with copper 1 chloride, you actually end up with in this kind of supramolecular dimers. And if you combine the neutral anions with copper 2, you actually end up in a different type of supramolecular dimers. And I'm going to show you what's the difference. First of all, these supramolecular dimers are very similar despite a completely different synthesis. There are also very peculiar interactions here between the pi-acidic central ring of the ligand and the SO moiety of the dioxothiadiazole, which persist in both supramolecular dimers. Here is a better view of this structure. So some of the ligands actually control the pi-pi stack interactions. The other ones are involved in sigma hole interactions. So I can already tell you that here all the ligands are non-radical, they are neutral. Here there is one radical, one neutral molecule per copper, and here all the ligands are actually in the radical anion state. So how did we differentiate that? So you cannot do that from the magnetic measurements. It's even not possible from the EPO measurements. But it's very feasible when you analyze the respective bonds of the dioxothiadiazole moiety. So we did that in our recent paper. We have analyzed all accessible crystal structures of neutral and radical species involving dioxothiadiazoles, and you can see then when you move from the neutral species to the radical anion, for example, the CC bond actually shortens a lot. The same happens with the NS, and the opposite happens with the CN and SO bonds. So simply by analyzing the bond lengths in the crystal structure of your compound, you can actually assign the valence state of the molecule. So in this case, in the case of the supramolecular dimers 1, the pi-pi stacking interactions are controlled by the radical anions, and these side ligands are actually neutral. In neutral dioxothiadiazole, the central ring is indeed very pi-acidic. That's why the part of the radical anion that has some electron density, additional electron density due to the radical, due to the additional electron that is placed on this molecule in the radical state, form this kind of very short interactions, 2.55. This is one of the shortest distances in this kind of sigma hole configuration. This becomes a little bit longer when these side molecules also become anions, but this actually shows that this kind of superconductor dimers, which are already 2-, are still very robust, and they hold together thanks to these weak interactions. I mean, interactions that are usually considered weak, but in this case, they are strong enough to keep these two molecules close together in this kind of superconductor dimer conformation. So after we identified where are our magnetic centers in these molecules, we managed to analyze the magnetic data for all these compounds. And we have also used some of DFT methods, which I'm not going to mention here, but we managed to calculate that the interactions between the radical anions in this pi-pi stacking conformation is very weak. And again, this is in contradiction to what we observed for simple salts, for potassium salt and PKN salts of some of our previous radical anions, but is in line that with the fact that the pi-pi stacking offset actually control these anti-ferromagnetic interactions between the pi-pi stack radical anions. So after that, we tested also 3-component compounds. So when you combine of the Dioxothiadiazole, the 110, the Awagas ligand with cobalt-2 and hexacyanoferrite, you end up with this beautiful trigonal molecule where we have 19 different metal centers, and it gets even more interesting because the side 3D metal centers are 6-coordinate, the inside the internal ones are 5-coordinate. So we already started a project where we actually rationally introduce 3D metal ions that have 5-coordinate preference, like copper-2, into these positions, internal positions, and the manganese-2 as the metal ions that have strong 6-coordinate preference on the outside positions. So this is not all that this is not where we stop with our Dioxothiadiazole project. What we actually want to obtain is a polydioxothiadiazoles, a molecule, for example, like this one. We didn't obtain it, but this is like one of our goals. They should show rich electrochemistry. They should be rigid, quite small, and multiple radical states, and possibly spin equals 1 state at some point. So what we have actually obtained and characterized are these two types of these dioxothiadiazoles. What is interesting about these molecules, they don't contain any hydrogen atoms, only heavy atoms, heavier atoms, but not lighter than carbon. We have characterized them structurally, so they are both obtained in the form of dianions. And here is the electrochemistry for both compounds. You can see that there are 5 valence states possibly accessible in these molecules, and 2 radical states with odd number of unpaired electrons, which leads to the spin 1/2 systems in the case of 3- and 1- molecules. And this actually we have confirmed for the 3-dioxothiadiazole compound like this one. So this is the pure spectrum for the monoanion. You can see the coupling between of the spin with the nitrogen atoms, and here you can see the spectrum of the trianion. It's featureless. We have actually recorded this spectrum in several times. Each time we couldn't see any coupling with the nitrogen atoms for some reason. So these are very preliminary results, not published yet. And we are still trying to understand this kind of spectrum for this compound. So we also obtained the crystal structures for this compound. So these compounds, these states actually are characterized structurally. And we also recorded the magnetic properties. In the case of the trianion, the properties are as expected for a spin 1/2 system, isotropic. In the case of the monoanion, there's something very strange happening. And this is even stranger in the view of that there are no pi stacking interactions for this molecule. The molecules, the spin 1/2 molecules in the crystal structure that I was talking about are well separated from each other. So we don't understand why there is this kind of decrease of the magnetic moment for this system. We also managed to oxidize our Dioxothiadiazole 2-, which is the starting point, to the neutral species. And the oxidation only occurs when the chloride ions are present in the solution. And this is probably because an extremely robust sigma Hall complex of this molecule in the neutral state forms with 2 chloride atoms with extremely close distance of 2.4 angstroms between the centroid of the central ring and the chloride ion. So in conclusion, I hope that I managed to convince you that the Dioxothiadiazoles might be interesting and have a lot to offer in the molecular magnetism. So they are easy to synthesize and show quite unique structure directing sigma Hall interactions. And polydioxothiadiazoles demonstrate multiple valence states, and the neutral tris-dioxothiadiazoles probably the strongest sigma Hall interactions ever reported. So I would like to thank the organizers, Matvey and Sergey, and everyone involved in the organization of the conference for the invitation. It's a great pleasure to be here. And obviously you for listening and for your attention. I'm eager to answer any questions you may have.
Thank you. We do have some time for questions. So if anybody wants to start. Artyom, please.
Okay, thank you, David, for your nice presentations, for nice radicals. I have 2 questions. One about, could you show slide 18?
18, right?
Yes, it's copper complexes.
I think it's this one. Yeah, no, copper complexes say. Copper complexes, not this one.
18.
Here. 18.
18, it's maybe.
Okay, 18 is about, yeah, this copper complex. Yeah, so you mean the chain, okay.
Yes, yes. So you, according to magnetic measurements, you have 1 spin of 1/2. And did you try to EPR study of this complex?
Sorry, to try what?
To try EPR study, electronic paramagnetic resonance.
No, I didn't try. That's a good idea. We should, I mean, it's already published, but we are still working on this system. And yeah, the EPR would be nice. We didn't do the EPR yet.
Maybe, I don't know, is there a localized spins? What is G factor value for these complexes? It's exchange broadened signal, or you
I
can
think it might be broadened due to this interaction.
Okay.
-1.8.
And another question on slide 23.
26, right. Yep.
Oh, 23.
23, sorry. Didn't hear it properly.
Yeah. The last radical, you have a KT value at low temperatures close to 0.18.
Yeah, that's right.
It seems that only half of radicals disappeared in your system, not all of them.
Yeah, so we explained that in the paper. So there are 2 types of dimers in this compound. So
yeah, strongly coupled and weakly coupled.
Yeah, the one pair is weakly coupled, the other one is strongly coupled. And again, this is probably due to the pi stacking offset.
Okay. Thank you.
Yeah, thank you.
We have a question from Sergey.
Thank you very much for nice presentation. I have probably educational question. Slide number 8.
3. No.
Number 28. Sorry.
28. 28. Yeah.
Yeah. So you told here that you analyzed all possible crystal structures.
I mean, all available in the crystal, yeah, in the database.
In the database. Okay. Thank you.
Yeah.
Okay. Do we have any more questions? Yeah, I also have a short one. So I wonder how you managed to isolate twicely reduced organic molecules. Was it chemical reduction, or was
You
it?
mean this ones? No.
Yeah, this one.
Oh, actually, for these molecules, the 2-, the dianion form is the most stable one.
Ah, okay.
Yeah, for some reason. I mean, that's how it is in this case. So
Yeah.
it means that if you increase the number of dioxothiadiazole moieties, you shift the whole electrochemistry towards higher values, and this is the most stable one.
Okay, clear. I think we have to move forward. Thank you again. And our next speaker, we're coming back to Moscow, so unexpected, from Institute of Kurnakov of Institute of General Inorganic Chemistry, Evgeniya Bazhina. Yeah, I see you. So go ahead, please.
Good afternoon, dear colleagues. Can you hear me well?
Yes.
First of all, I would like to thank an organizing committee for the opportunity to present the results of my research at this conference. Let me start my presentation. Coordination compounds of chromium-free, in which a metal center contains free and paired electrons and generally has an octahedral coordination environment, are of interest mainly due to magnetic and photophysical properties, which determine their importance in the design of single molecule magnets, magnetic coolers, and their application as luminophores, dyes for solar cells, and photoredox catalysts. Carboxylate ligands are widely used for the synthesis of paramagnetic compounds due to their coordination diversity. In particular, anions of malonic acid often exhibit alkylating coordination and form with metal atoms stable bis and triskylate units, which can be connected to other metal centers via two carboxyl groups in different bridging coordination modes, giving rise to polynuclear molecules and coordination polymers. The existence of substituted analogs of malonic acid makes it possible to affect the structure of the obtained compounds by varying the substituent at the carbon atom. In the present work, we used dimethyl malonic acid as a ligand, and the aim was to study the reaction of chromium-free with barium salt of dimethyl malonic acid to reveal the influence of the initial reagent ratio and the starting inorganic salt on the structure of the compounds formed, and to investigate their magnetic properties. The reaction of chromium nitrate with barium dimethyl malonate taken in a ratio of 1 to 3 in an aqueous solution gave the crystals of a one-dimensional polymeric compound composed of binuclear anionic units, in which two chromium atoms are linked by two bridging hydroxyl groups. Each chromium atom is coordinated by two dimethyl malonate anions in a chelating mode. In the crystal structure, these binuclear units linked to each other through barium atoms, which are coordinated to carboxylate oxygen atoms and hydroxyl groups to form polymeric chains. Each barium atom is additionally coordinated by free water molecules. The use of chromium chloride instead of nitrate in the similar reaction had no effect on the structure of the reaction product. A similar reaction with an excess of dimethyl malonic acid led to formation of the two-dimensional polymeric compound constructed from mononuclear anionic units in which chromium atom is coordinated by 2 malonate dianions in chelate mode and 2 monoprotonated malonate anions in a monodentate mode. Barium atoms are linked to each other by bridging water molecules and by nitrate anions. Coordination environment of barium atoms complex with free water molecules. Two-dimensional polymeric structure of this compound is formed through the binding of these units by barium atoms, coordinated by carboxylate oxygen atoms and of the dimethyl malonate ligands. The analogous reaction, but with chromium chloride as the initial salt, afforded crystals of the new compound exhibiting three-dimensional polymeric structure. This structure formed by 2 types of mononuclear anionic units. The units of the first type are similar to this of compound 2. In the second type of anionic units, chromium is coordinated by 2 chelating dicarboxylate dianions and by 2 water molecules. In the crystal, these units of the first and second type are linked together through coordination of oxygen atoms of malonate ligands to barium atoms to form a honeycomb framework structure. Barium atoms are linked in pairs by bridging water molecules. The temperature dependencies of KT for compounds 2 and 3, which contain mononuclear chromium units, are similar in shape. At 300 kelvins, KT values are in good agreement with the theoretical value for one isolated chromium ion. The KT value remains unchanged with decreasing temperature down to 10 and to 16 kelvins for compounds 2 and 3, respectively, indicating an absence of meaningful exchange interactions between chromium ions. And then below these values, KT monotonically decreases to minimum value at 2 kelvins. These data are consistent with X-ray diffraction data because the direct distances between chromium ions are too long to provide effective exchange interactions. According to DC magnetic measurements for compound 1, KT value at 300 kelvins are in a good agreement with the theoretical value for 2 isolated chromium ions, and in the temperature range from 300 to 7 kelvins, the KT value increases, but below 7 kelvins, a sharp decrease in KT value is observed. The theoretical interpretation of the experimental plot KT versus T gave following best fit parameters. To confirm the obtained magnetochemical data, we perform DFT calculations for this compound. As evidenced by the shape of the natural magnetic orbital of the dinuclear anion of compound 1, an antiferromagnetic exchange channel is absent, resulting in the appearance of ferromagnetic interactions between 2 chromium centers. The estimated value, J value, is in agreement with the magnetochemical data. The search on the literature data of the chromium-free complexes containing the dinuclear hydroxybridged unit shows that antiferromagnetic exchange interactions dominate in the majority of these complexes. Ferromagnetic exchange interactions were observed only in 2 known malonate complexes, like in our complex 1. An analysis of the literature data shows that the value of the character of the exchange parameter J depend on chromium-chromium distances and chromium oxygen chromium angle and chromium oxygen bond length. In order to determine which of these parameters exerts a stronger effect on the character of the exchange interaction in complex 1, we perform additional DFT calculation, including variation in metal-metal distance, which led to the change in the chromium oxygen chromium angle at the constant value of oxygen distance. As can be seen from the table, weak antiferromagnetic exchange interaction, weak antiferromagnetic exchange due to the presence an exchange channel was predicted in the case of chromium distance of 2.9 angstroms and the angle of 96.8 degrees. When the metal-metal distance was fixed at 2.9 angstroms and the angle was kept equal to 99.3, like in structure 1, the value of J was positive. When the chromium oxygen chromium angle was fixed at the value of 96.8 degrees and the chromium distance was kept equal to 3.03 angstroms, like in our complex, the calculated exchange constant was indicative of weak antiferromagnetic exchange. Therefore, it can be concluded that the angle chromium oxygen chromium rather than the distance chromium has a greater effect on the character of the exchange interaction in compound 1. According to AC magnetic susceptibility measurements, complex 1 displays slow relaxation of the magnetization in external field. The frequency dependencies of the AC magnetic susceptibility were measured in the optimal field of 1500 oersteds in a temperature range from 2 to 8 kelvins. The best fit of the experimental dependence of relaxation time on inverse temperature was achieved by involving Raman mechanism and quantum tunneling of magnetization. The EPR spectrum of solid samples of compound 1 measured at room temperature is described by contribution of one complex, whereas the EPR spectrum of compound 3 is described by the sum of contributions of two complexes with different parameters, which is consistent with the X-ray diffraction data. Parameters of spin Hamiltonian for compounds 2 and 3 obtained from the EPR experiment are presented on the slide in comparison with the values obtained by ab initio and DFT methods. We can see that these computational methods provide reasonable agreement with the experimental data. The EPR spectrum of compound 1 has a complex shape. It is described by contribution of two interacting mononuclear units in 3 different spin states. The best fit zero field parameters are presented on the slide. These parameters were also calculated by DFT method. For complex 1 with spin state 3, which corresponds to the ferromagnetic coupling of chromium free ions in dimer, the D parameter value was in a good agreement with the experimental results. At the same time, the obtained values for other spin states of this dimer differ strongly from experiment. The observed inconsistencies can be explained by the high rhombicity of the system, which complicates the determination of the sign of the D parameter based on the quantum chemical calculations. In conclusion, the variation of the mole ratio of the acid to hydroxide, as well as in the nature of the initial metal salt in the system under investigation, can give rise to barium-chromium coordination polymers containing 3 structural types of chromium carboxylate units and exhibiting different arrangement in crystal. Compound 1, composed of binuclear units, exhibits ferromagnetic exchange interaction between chromium ions, and this is the third example for chromium-free malonate complexes. The DFT calculations for the binuclear unit in complex 1 show that the chromium-oxygen-chromium angle is the main factor responsible for the type of the exchange interaction between the metal centers. Thus, the exchange integral J increases with increasing angle. In addition, compound 1 demonstrates field-induced slow relaxation of magnetization, the origin of which is a magnetic anisotropy confirmed by DFT calculations. In conclusion, I would like to acknowledge my colleagues who was involved in this work, Russian Science Foundation for the financial support, and thank all of you for your kind attention.
Thank you. Now we're ready to proceed to the questions. Is there any? So perhaps I will start. So this three-dimensional polymer that you obtained, so it looks like it has some pretty sizable pores. So did you try to characterize the internal volume by porometry or some other approach?
Yes, the pore volume is in compound 3 is about 7%. It was measured by mercury software. These pores are filled with water molecules, and when we heat this compound to remove the water molecules, it was found that the structure of these compounds degrades. And when we try to measure the sorption properties for this compound, it turns out that it was no sorption because of degrade structure.
Okay, thank you. Do we have any more questions? If not, we will proceed. Thank you again. And the final talk of this section will be given by Sergey Konchenko. We're moving to Novosibirsk, and he will talk about MD4F metal complexes. So you have a floor, please.
Здрасте.
Hello.
Меня слышно?
Yep.
Да? Так, а как тут запуститься-то?
Green button share screen at the bottom of the screen.
Так, green button demonstration.
And choose your PowerPoint presentation in the open window. Perfect.
Так, все пошло, да?
Just start slideshow so we can see it full screen, if possible.
О, ура! Получилось. Yeah, exactly. You said that you all moved to Novosibirsk, but I am here in Nizhny Novgorod. Simply, I really, let's say, believed that this conference will proceed in Nizhny Novgorod. So I've passed about 3,500 kilometers by car to visit my friend Igor Fedyushkin, and just now I am here. in not far, let's say, from Nizhny Novgorod. So you may move to Novosibirsk. I'll start my presentation from here. And first of all, I of course want to say that I represent Nikolaev Institute of Inorganic Chemistry from Novosibirsk, and that's my research group in this institute. It's titled as Laboratory of Polynuclear Metal Organic Compounds, and you see that that's quite young laboratory, except of me probably. And we are very active in constructing really unusual compounds. And one of the topic, one of the subject of this, one of the project of our laboratory concerns lanthanides. And today I'll tell you about mixed DF metal pnictides and chalcogenides, which we obtained in our research group and also in cooperation with German research groups of Professor Peter Royski and Manfred Scheer. And more or less the most important part, the most important aim of this talk actually to introduce these compounds to, let's say, magnetic community, and maybe to find some partners who are interested in measurements and let's say studying of these compounds or something similar. Okay, so for beginning, holometallic molecular lanthanide pnictides, what they are. Actually, that's a very rare, very small class of compounds. And before 2009, when we obtained the first when we obtained the first polyphosphide of samarium, before that, only two compounds were known, obtained in 1991 and 1992 by, let's say, present, I think, leader of lanthanide chemistry, Willy Evans. And all these compounds, as you see, are very similar to such funny toys as these spinners. Actually, we have part of pnictide or polypnictide as a nuclear of these complexes here, and this anions, this polypnictide anions surrounded with lanthanide containing complex fragments. That's homonuclear, exactly lanthanide pnictides. If we want to go further to mixed metal, we have to add or to substitute some lanthanide containing labels of this toy, yeah, to D metal complex fragments, like it's shown here on the right toy. To do that, let's say it's not very easy. Actually, before 2009, nobody knows, nobody known about this. Nobody knew about such complexes, and actually, it was really interesting and really hard work to create synthetic methods, synthetic approach to these complexes. And the most productive, the most fruitful method was actually found this reductive, so-called reductive approach. When we use samarium or other lanthonide-based complexes in low oxidation state, and then reduce some appropriate, let's say, phosphor or antimony or arsenic sources, yeah, and finally we have we construct something very nice, very interesting, which is looking exactly as these toys which I showed. Yeah? That's some nuclei of Pnictide atoms and lanthonide cations surrounding this nuclei. Actually, we have really a redox reaction. Samarium-2 in this case is reducing agent, and phosphorus is oxidant. Of course, if you want to prepare compounds with not only with lanthanides but heterometallic ones, then we can let's say we can use as oxidants not simple compounds, simple sources of phosphorus, arsenic, or other pnictides, but to use complexes which already contain some pnictide groups and also transition metals. Transition metals such as iron, molybdenum, cobalt, and so on. Actually, at present, a lot of such complexes are known, and actually, that's more or less the main subject, the main topic of Professor Manfred Scheer, who was involved in this chemistry, exactly in this project. Let's say exactly because he had a lot of such complexes, and also a very strong, very good experience in working with them. So we can use lanthanide-2 compounds and let's say oxidize them with this polypnictide transition metal complexes. That's really fruitful. This approach really fruitful. You can see some complexes which were obtained in this way. For example, this one contains 2 samarium atoms and 2 iron atoms, and P10 fragment in between. In this case, we have lanthanides, samarium or ytterbium, and also 2 molybdenum atoms, and P6 fragment in the middle. And here 2 cobalt and samarium, and P4 or arsenic 4 fragment. And it's very interesting that in this case, we were able actually to obtain all these compounds for all pnictides, for phosphorus, arsenic, and antimony. So if until 2009, look here, you can see that there were no any examples of such complexes. Yeah, you can see that at present, or let's say at least last year, the situation changed dramatically, and mainly because of let's say works of this team. Yeah, actually, the only thing which is looking quite, let's say, boring. In this case, we have only samarium and sometimes ytterbium complexes. We were unable to go further to other more interesting lanthanides to get more interesting properties, magnetic properties, first of all, is, of course. Yeah, and that's actually arises from the knowledge that only three elements, that's, let's say, school knowledge here, or student knowledge, that only three metals, samarium, terbium, and europium, really have stable oxidation state too. The situation changed dramatically last few years. Actually, for the second series of elements which were found to have really, let's say, quite stable oxidation state too, were thulium, dysprosium, and neodymium. And recently it was shown that for all lanthanides, except of promethium, it's possible to obtain complexes in this oxidation state too. So all lanthanides might be involved in this chemistry. Another variant is to use redox active ligands. In this case, we have complexes of lanthanide 3 and redox active ligands such as N2, 2-, for example, or this well-known Bian from Igor Fedyushkin, which is charged also 2-. And also interesting variant was shown by Paola Diaconescu. She used naphthalide and anthracite complexes like this shown here, where aryl is actually a reducing agent. So in this case, lanthanides do not change oxidation state, but oxidation state as a reducing agent ligand serves. And the last variant is this compound, the left one, was obtained by Trifonov's group. And actually, in this case, we have a pair of reducing agents in one molecule. We have element, metal, lanthanide in oxidation state 2, like in the left example and here also. And we have also aryl charged 2-. In this case, it's benzene, and here it's naphthalene. So altogether, all these compounds can be used for, let's say, covering whole row of lanthanides to obtain similar compounds. For example, let me show. For example, that's our previous work when we obtained a compound with iron and samarium in one molecule and P10 ligand that was published in 2013. Yeah? That's quite usual already compound with samarium. But recently, using all these complexes, which I showed to you with redox active ligands and also with unusual oxidation state 2 compounds, we have obtained almost whole set of lanthanide complexes containing lanthanide and iron and phosphorus in one molecule. Then, in some cases, we have found that it's very dramatically changed. We have found a very dramatic change of direction of the reaction. For example, if we change CP star with more bulky substituents, with more bulky CP, then oxidation goes in other way. In this case, lanthanide connects to phosphorus, but also carbon attack phosphorus of the same molecule. So that's more or less we observed CH activation in this case. So new lanthanides, new compounds show us new possibilities, new ways for construction of very unusual complexes. To be honest, that's the only complex for dysprosium which we measured at least for magnetic properties, and it was found that since it's dysprosium complex, of course, it exhibits magnetic molecular magnetic properties, but very let's say not interesting. Yeah. Okay, that was about Pnictides. Now about Chalcogenides. I would say Chalcogenides are more wide distributed than Pnictides. So different structures were obtained before our works. But what is interesting, we can see different kinds of polypnictides inside the molecules with these lanthonide complexes. Yeah, and that's they all also tend to be cluster compounds. For example, this one compound was obtained, we reduced by ytterbium or samaracin, simply sulfur. And let me show that more, let's say, thoroughly. In this case, we see that both samarium-2 and ytterbium-2 reduce sulfur, and we have this cluster, triangle cluster, with S4 ligands on each edge. And also, it's possible to prepare, of course, heterometallic complexes which contain both D and F elements. For example, in this case, that's iron and samarium or ytterbium. So by reducing with lanthonide 2 this iron disulfide, we obtained these nano wheels. And of course, in this case, it's also interesting to go further for new metals, for more interesting metals from the point of from magnetic point of view. Yeah, and shortly I introduce our last work concerned with vanadium complexes. These complexes, which are shown here, were involved also to redox reactions with some samarium and ytterbium complexes. Here you can see ytterbium example. In this case, always we have exactly mixture of products, but using powder diffraction in combination with single crystal diffraction, we can make quantitative analysis, and we know that the major product in this case is this compound 2. So it's possible to isolate it even if they have very close solubility. In this case, we can see other examples. Some of them are quite interesting. For example, this one, that's 2 cubes, which coordinates via sulfur to ytterbium complexes. And shortly, I show just some other interesting structures, which all tend to be cubic. So that's in every case, that's cubic of vanadium and sulfur, for example, and thulium. Yeah? In this case, thulium lost his CP at all, and you see 2 cubics connected with each other. It's interesting also that these complexes, if we calculate oxidation state, we see that actually oxidation state is, let's say, we have different mixed oxidation states. For example, vanadium 3 and vanadium 4. These complexes are known for samarium and ytterbium, but using some other methods, it's possible to prepare complexes also with, for example, dysprosium, neodymium, gadolinium. So wide a variety of complexes can be obtained by our methods. And I invite people to, let's say, to pay attention to this talk, to this compounds, and maybe somebody will want to collaborate for studying and measuring these complexes and I mean magnetic properties there. And what is very important, I am searching, we are really searching for people who can measure compounds which are very, very sensitive to air. That's the major disadvantage of this complex. They are really very sensitive. So that's more or less all what I wanted to tell you today, and I stop my demonstration for that. Thank you for your attention.
Thank you very much. We have time for questions. So who would like to start? Well, let me be the first one. First of all, you have absolutely beautiful compounds. I just can't imagine how much effort goes into synthesizing it. And what is surprising for me, so you said that you only characterized from magnetic point of view your dysprosium complex with CH activation. So that's the least symmetrical one. So it's the one which is expected to have the worst magnetic properties. And you have so many other compounds which looks like they could be good SMMs. So why you haven't studied them?
We just searching for somebody who help us with that.
I think there are plenty of people here who should be interested. We don't have magnetometer, but I think these compounds should be good SMMs, I think. So that's my impression.
Yes, I think that there is a lot of interest in what we can see, but what we can find. But let's say I'm searching for somebody who are interested in that.
Okay. Do we have any more questions? So I can't see any. Okay, so let's thank all the speakers of the session again. And we are going to come back in 20 minutes at 3. So now we have a coffee break. Please come back.